Hello, welcome everybody to the first session of Student Talk. Before we begin, I would like to mention that we have prizes for the two best student speakers. So, yeah, keep your. So the first talk is by Juhi, and she will be talking about bribery. First student talk is. Okay. You are eligible for the prize.
So, thank you everyone for coming. And today I will talk about my paper titled Parameterized Analysis of Bribery in Challenger Chess Tournament. So, this is a joint work with Henrik Molde and Miraj Jihavi, both from Bengali University of the Negev, Israel. And this work recently appeared in Ichkai 2024. So, let's start. What is tournament? So a tournament is a method to determine the winner of a competition based on pairwise comparisons. The best example for that would be sports competitions. As we can see from the recently concluded Olympics and World Cups. So to carry out tournaments, there are many formats available in the literature. So, for example, in single elimination tournament, there are n players in the first round and they are paired up and only half of the players go to the next round. And in log n rounds, we have a winner. There is double elimination tournament where a player has to lose at least 2 matches to get knocked out from the tournament. And so in the first round, when half of the players gets knocked out, they went to the loser bracket, and then they compete there. And in round robin tournament, so there are n players, and every player plays with all of the other players. So this is very good because we get more data that who is stronger and who is weaker. But if the number of players and number of teams are very much, then we have less resources. So this is not a good tournament there. Then we have Swiss system also where so this is like round robin, but here in this system, we limit the number of rounds that we can play. Then there is this ladder system where players are put in the levels of a ladder, and players on the lower ladder can challenge the player on the upper ladder, and there are some restrictions that you can challenge up to a certain point in the ladder like this. So every tournament has their pros and cons. But today, in today's talk, we will talk about Challenge the Champ tournament. So what is that? So this is a very simple but popular form of sports competition, and it's usually used in the WWE Championship, and it is also known as defending the title. So what is this competition? So in Challenge the Champ, we have n+1 players, and initially one of them is the initial champ. Then some player come and challenges this champ, and if the challenger wins, he becomes the current champ. Otherwise, the champ remains the same. And after all players have challenged, then the player in the last round becomes the current champ. So let's take the example. So here in round 0, E star is there and he is the initial champ. Now E1 comes and challenges E star. So in round 1, E star and E1 plays, and whoever wins is the champion in round 1. Then E2 comes and he challenges the winner, and whoever wins becomes the champion in second round. And when all these n players have challenged, so in round n, whoever is the winner becomes the ultimate champion. So here we can see that this is the seeding. So in which order these players are coming and challenging matters, because right. So this is the seeding, and this is the format. Challenge the champ. Now note that every player wants to become the champ, right? And with the rise of social media and ongoing monetization in sports, so the stakes become too high, and it intensifies the competition. So what happens? Tournaments are prone to manipulation, and a significant body of research has already been done in computational social choice, where people study manipulation in tournaments. And most natural way to manipulate a tournament is to offer bribes, right? And one of the practical assumption is that we have a budget, right? We cannot buy everyone if we want someone to win or lose. So we have a budget, and other practical assumption is that different factors involve different costs. So if I want to make someone win the competition, maybe if I want to bribe the coach, it will have some different cost. If I will want to bribe the judge, it will have some different cost. And if I am bribing a player, then bribing a team, then I may want to bribe only a certain subset of players. So having different cost with different does make sense, right? So the problem that we study is bribery in challenge the champ tournaments. So here, what we want to do, we want to make sure that the initial champ win, and for that we will offer bribe to the challengers, and there will be a given threshold, and we want that the probability by which the initial champ win is above this threshold. So note that whenever two players compete, so the outcome can be deterministic or probabilistic. So both models have been studied in the literature, but here we will focus only on the probabilistic model. So if we talk about the formal setting, so for every challenger, we know the probability by which our initial champ, which is a preferred pair denoted by E star, with which probability E star is gonna beat this challenger E. And for every challenger E, we have a bribe vector CE. So if a challenger E accepts LE bribes, then this bribe vector will have LE quantities, LE elements, and in every element we have a tuple which represents the bribe that he is going to take and the probability with which he is willing to lose. Not that any player can only underperform, right? If he takes bribe, he cannot perform better. So this tuple represents the bribe that he is taking and the probability with which. So initially, if he is losing with probability say 0.6, now he will lose with probability 0.7 or something like this, more probability. And we can assume that the bribe vectors are monotone because this makes sense. If I am offering you say 100 euro bribe, then I want, and if I am offering you 200 euro bribe, then obviously it makes sense that you will do that, means worse in this case if I offer you more bribe. So we assume that bribe vectors are monotone. Now, so this is the setup, and this is the formal definition that in the input we have an initial champ, we have n challengers, we have a winning probability, and the bribe vector for each challenger, we have some budget, and we have a probability threshold. And the question is simple, that can we bribe the challengers without exceeding budget B such that the winning probability of the initial champ is at least T?
Once the player loses a game, they are out of the competition.
Yeah, they get out of the competition. Yeah. So this is a knockout tournament. You play, you lose, and you get out of the tournament.
Sequence is fixed.
Okay, so the sequence is, so different sequence lead to different outcomes, but we will see the problem that we will also observe it, that it is application in other thing also, that here the sequence does not matter because ultimately E star wants to beat everyone with high probability. So it does not matter if he is competing with E1 in the first round or E2. So in this particular, so in general in challenge the champ, the order of the challenges matter, but here in this setting, it does not matter. So non-results of this problem. So this problem was introduced by Mehta et al. In the year 2015. There they showed that this problem is XP when parameterized by the number of players. What does it mean to be in XP? It means that there exists an algorithm that solves this problem in this much running time, where n is the input size and fk is some function of this parameter k. And they also showed that there existed pseudo-polynomial time algorithm for this problem. So the immediate question that comes into our mind is that, is it weakly NP hard? So we proved that yes, this problem is weakly NP hard. If we take, yeah.
So you said it was parameterized the number of players.
Hmm?
So the number of players is n. The algorithm takes n to the power fn time.
But here we want, so here every player has to perform some action. So for every player, there are some k options that he can take.
What is K exactly?
K is the number of players. N is the input size.
What is the input?
So input size also has like the number of players and the other things. So it is n, but so, okay. So
just any here, right? The number of possible priority levels for each player. Can you describe the input?
the input is this. So k is the number of players. So see that for every player we have some k options, right? And these options can be humongous because a player has to take many options. This the number of bribes that a player can take can be much more than the number of players.
Maximum player. Can you just go back almost like?
Okay.
Yeah, this one. Price the maximum.
So this is
Is K the maximum of the LD?
k is the number of players. So we are trying to ask if the number of players are bounded, they are small. Can we say anything positive?
Number of challenges in players at the same time.
Yes.
N was the number of
Is the number of tries. I think n can be much less than LE.
Yeah. So
Yeah, so-
N is the maximum of the LD.
No, n can.
N is the number. And
I
K,
want-
and K is the maximum of the LD.
Yeah, so the number of players can be much less than the size of the input because in the size of the input we have these bribe vectors also.
Can you just go to the case slide where you talk about this?
This
Okay, yeah, so, if you will talk about, I mean, so here she is defining it. K is equal to N for power.
Okay.
yeah, this is the definition for
K is
x.
equal to N and N is replaced by the input size.
Sure.
Okay.
Sorry.
Okay. So talking about our results, so first we prove that this problem is weakly NP hard, and then we prove that this problem is W1 hard when parameterized by the number of players. So this
Maybe you said this in the beginning and I missed it, but it's all this legal. Can make.
You will use your algorithm to say.
It's legal and bribe is large now.
maybe we want to see that what can happen, so we can catch that who is bribing. So we can think about it in that way. So we first prove that this problem is W1 hard. So for those of you who don't know what is W1 hard, so it means that under certain assumption the problem is not FPT, which is fixed parameter tractable, and which means that when parameterized by K, there does not exist any algorithm that solves a problem in this much running time. So in parameterized complexity, we seek FPT algorithms where we say that for this parameter, the exponential drop is allowed only in this parameter. For the rest of the input, this should be polynomial in time. So we prove that if parameter is the number of players, then this problem is W1 hard. Then we consider another parameter, which is the number of distinct bribe values, and we prove that this problem is FPT with respect to this parameter.
It seems to have the like limited number of bribe values, and the scale of n also reduces, right?
No, may not be because say the number of players are more, but all they are offering is very less number of bribes. So this is also possible.
Okay, so in this case, you no longer have the appropriate base, right? So case out now, the new parameter is the bribe.
So these parameters are like not dependent on each other. It may happen that the number of players are more, but the distinct bribe. So this is distinct, not the number of bribe. So the distinct bribe values are less, and it may happen that players are small, but they offer many bribes. And next is that when we consider the parameter to be the number of distinct probability values, then also we prove that this problem is fixed parameter tractable. So before moving to the technical part, I just want to mention one application in campaign management. So as you have noticed that the order of the challenges in this problem that we are considering is irrelevant.
Sorry, just one more question. Just go back. So when there are n players and there are k different bribe levels for each, fixed K. Or sorry, let's call it R. There are R different bribe levels for each. So this does not exclude a n to the R time algorithm. Right?
This does not exclude. No, because we have proved that
It
it's
is
FPT. It is FPT. So it has algorithm. If it has FPT, then it is XP also.
It's better than.
Yeah, it is better than XP. Okay.
So what is weekly?
So weekly NP hard means if the okay, so we see that there is a result which says that its running time is this much. So if B is unary, then it is polynomial time solvable. But if B is binary, then this is not polynomial time solvable. So we say that okay, if B is binary, then it is not possible to get this as running time. This weekly NP hardness result. So this has application in campaign management also, because here, like, if we can think E star as a candidate or a product or idea something, and these EIs as voter or approver that we whose what we want to achieve, then the price probability pair for every player. So we can just think that how we are going to bribe these voters or approvers to win their, like, how should we distribute this bribe among these approvers so that so that we can win their confidence. And so this comes as an application in campaign management, and more work on campaign management can be seen in these works. Now let's move to the technical part. So first, when the parameter is the number of players, we give reduction from product knapsack. So first, I would like to tell that why this parameter makes sense, because in practical scenarios, you see that in any like tennis competition or boxing championship, like in every sport, the number of players that participate are constant, right? So this makes a practical parameter. And we give reduction from product knapsack. And what is that? So it is just like the usual knapsack problem that you have seen, that there are a set of items with weights and profits. And here we want to fill a knapsack such that its capacity is C and value is V. And the only difference is that here we want to see that the value of these items, their product is at least V, such that their weight, the summation of their weights is bounded by the capacity. The only difference with the usual knapsack is that here we are taking the product. This is the product knapsack problem. So, so if we see the reduction that we had in mind to give the reduction, then that only proves the weakly NP hardness. But we wanted to prove the W1 hardness. So for that, we prove this theorem that says that product knapsack is W1 hard when parameterized by the number of items in the knapsack. And to prove this theorem, we give the reduction from small k sum problem parameterized by k. And it can be noted that this result may be of independent interest. So this is a theorem. Now notice that when you want to give the reduction from product knapsack problem to our problem, then it may not work exactly, because here, if you have noticed, we have shown that product knapsack is W1 hard by the number of items in the knapsack. If we want to give the reduction that we had in mind, then we will prove that our problem is parameterized by the number of players that we bribe. So we want to avoid that. So we apply the color coding technique and prove that the multicolored version of this problem, that is multicolored product knapsack problem, is W1 hard when parameterized by the number of colors. And what is multicolored product knapsack? Here, the only difference is that initially we have some color classes, and every item is distributed among these color classes, and we want a solution which has an item from each of the color, exactly one item from each color class, which satisfy these conditions. So what is the use of this? So if we give the reduction from this, now if we give the reduction from multicolored product knapsack, then our parameter will get mapped to the number of players. And yeah,
W1 hard, this does not hold for the regular knapsack.
it's whole, but the statement of our problem, it involves the product of probabilities. So, but there it is summation. So, but here we wanted product, and you may say that we can take log, but that did not work. So we had to use this product knapsack problem. Like usual knapsack does not serve our purpose here, because in our problem we want the winning probability of E star, which is the product of probabilities that E star we. So we need the product.
So, just continuing the discussion, general knapsack is known to be W5.
Yes. So, okay, so this is the brief idea of the reduction. So if you, I think till this point, you must have understood how we have come up with the reduction. So in the input, we have these color classes where the items belong, and we have this budget of the knapsack, and we have this value, and every item has some profit and weight. So we did the reduction. So the player set has all these. So for every color class, we have a player EI, and we have this favorite player E star, and the bribe vectors are arranged in such a way. So for every color class, we have some items with some bribe and with some value and weight. So we just take that and make them the bribe vector for the player EI, and we set the budget as same and threshold as the value, and it is easy to see that this result will hold, right? So now let's move on. Okay, so this has an interesting corollary for knockout tournaments as well. So this is a little detour because we are talking about challenger champ tournaments only. But this is interesting. Why? Because if we want to give a usual NP hardness, then this should not work, because in challenger champ tournament, if we have n players, then when we take this instance to construct an instance of knockout tournament, then the number of players becomes 2 to the power n. So there is an exponential blow up. So there is no way to come up with a polynomial time reduction. But here the parameter is the number of players, so we can do that, because in parameterized complexity we are allowed to exponentially blow up the parameter, and here the parameter is the number of players. So we also proved that constructive bribery for knockout tournaments is W1 hard when parameterized by the number of players. Now let's consider the parameter, which is number of distinct bribe values. So why this parameter makes a good parameter? Because every price section has the same value, right? If I am if there is some judge or some coach who is willing to take bribe, then he will have some different some fixed price, right, or a set of range of price, right, which he is willing to take to modify his decision, and it will not matter to him much that who is playing. So he will, if he is corrupt, right, and he will have some budget. So he will have some bribe values that he is willing to take. So this is also a practical parameter, and to prove this that our problem is equity with respect to this parameter, we give reduction to mixed integer linear programming problem. And what is that? It is just the usual linear programming problem with addition that we have some constraints and we have some variables. Here the only thing is that we say that some of the variables should be integer. And the question is that is there an assignment to the variables such that these constraints are satisfied and the variables that were supposed to be integers are integers. And there is a very nice result by Lenstra in which they prove that MILP is FPT when parameterized by the number of integer variables. So then if the number of integer variables that we demand are small, then this problem is FPT. So the proof idea goes like this. We formulate our problem to an instance of MILP, and then we prove that the number of integer variables that occur in that MILP are upper bounded by our desired parameter, which is the number of distinct bribe values in this case. So how did we define the MILP? So if K is our parameter, which is the number of distinct bribe values, V is the set of distinct bribe values, then V prime is a subset of V. Subset of V means this is the set. So if V are the number of distinct bribe values, then V prime denotes a set of bribe values that a player is willing to take, and U prime is a particular value in V prime. So for this pair, so for every value U prime in a given set V prime, we introduce a variable, and this is an integer variable which says that how many times we use this value U prime to bribe a player whose acceptable bribe values was this set V prime. And also P denotes the probability profile of a player. Then note that players are uniquely characterized by their probability profile and their set of bribe values. So what do I mean by that? We know that the bribe vectors are monotone in nature. So if I give you a set of bribe values and I give you a profile, so the profile will have the same number of elements in the bribe vector. Now, if you know that which u prime I am talking about in this bribe vector, then you can just relate that with which probability it corresponds to. So we need not consider every pair of u prime and p prime from this probability profile. We can just say this is the probability profile and this is the u prime. So with this triplet u prime, v prime and p, you can come up with this probability p. And for every this triplet, we have this variable xp u prime v prime, which are rational valued variable. Counting the number of times we are using this bribe value u prime corresponding to the probability profile p, and this set of bribe values v prime. And we want to maximize this objective. So this objective captures that how many times we are using the bribe value u prime, and the probability p is the probability corresponding to that, and we are multiplying those. We want to maximize this, and these are the constraints. We have 4 constraints. In the first constraint, we want to maintain the budget, and in the second, we want to say that okay, u prime is used by these variables and u prime is also used by these variables. So we want to say that for every probability profile that corresponds to that set v prime, their summation is equal to the x u prime v prime. And another is that we do not want to use one variable too many times. So we have this constraint. And lastly, we want non-negativity constraints. So what we have done, we have written down an MILP for our problem, and we have bounded that, okay, so the total number of variables and constraints are bounded by this much, where k was the cardinality of the set V, and the integer variables are also bounded. So this is what we wanted. So by using Lester's result, we can say that our problem has an FPT running time with respect to the number of distinct bribe values. And okay, so this, and for the, yeah.
So you get double exponential.
Yeah. Yeah, so the running time is not single exponential here. So this is one of the open problems that we have. So this, the algorithm I provided was for number of distinct bribe values, and by similar formulation, we can prove the problem for number of distinct probability values. And in the conclusion, I want to summarize that we have some new parameterized result for natural bribery setting, and we prove the W1 hardness of product knapsack parameterized by the number of items in the knapsack, which may be of independent interest. And in the future, we can ask that can FPT results be improved to single exponential running times, and how to generalize these results for other tournament models, because we have seen that this has some application, like we have some results for knockout tournaments as well. So for other tournaments that I mentioned in the initial slides, can we extend the results there? And this is the link to the paper if you want to read. And these are some of the references. Thank you.
Thanks, Juhi. So maybe you have time for one quick question. Yes.
So the mix into the linear program, FPT algorithm for it, how bad is it the parameter? Is it simply exponential or is that itself doubly?
It is definitely doubly, but I don't know if it is more worse than doubly exponential. Like I think it's doubly.
She has already given the order.
Like I'm not sure about that.
Okay, so if there are no more questions, let's thank the speaker also.